So we spent chapter 10 and 11 talking about energy and different kinds of energy and how energy can change from one form to another, and it's never created or destroyed, it's only changed. This chapter we're going to specifically look at thermal energy, which is something we've started to talk about, and last lecture we talked about being able to put heat into a system to make that system do work. Or we could also take heat out of a system, and that would be a value of negative Q, and putting heat in would be a value of positive Q. And this is a way for energy to be transferred between systems. And so if I add heat to a system, then I am ultimately adding energy in the form of thermal energy. Right, and that's just measured in joules. And so we're going to explore this idea of the thermal properties of matter and how adding heat to a system can change that system. All right, and you guys probably all remember this from middle school. To explore the idea of how heat affects different stages of matter, we first have to look at the three stages of matter: solid, liquid, and gas. There is plasma, but we're not going to go into that today. And so when we think about a sample of a solid, we tend to think of these atoms as very closely spaced and kind of vibrating back and forth, and so they have a very low kinetic energy and a very low, because of that, thermal energy. Right? They're just kind of hanging out there. We tend to call solids frozen states of matter. And so while you might not think of your desk as being frozen, it technically is. These things have a fixed volume and a fixed shape. And a fixed shape. Good. And then if we add heat to the system in the form of, then we increase the thermal energy, and that solid is going to melt and it's going to form a liquid. And in a liquid, those atoms begin to move around just a little bit more, and that's what gives liquids their nice flowy property. And they have a little bit more thermal energy and a little bit more kinetic energy. So I'm going to describe that as medium kinetic energy and medium thermal energy. All right. These things have a fixed volume. But they do not have a fixed shape. Liquids take the shape of whatever container they're in. And then finally, if we continue to add heat to that liquid, we're going to get a gas, right? And gases have no fixed shape and no fixed volume because those particles really begin to fly out and spread around. They can go wherever the heck they want, and they can go there really fast. And so I'm going to describe this as high kinetic energy and high thermal energy. Right? And so this is just a basic model of all matter in our universe. Depending on what type of matter we're talking about, the temperature at which things are a solid, liquid, or gas differs, but all matter has the capability to go through these stages. And then likewise, if I take heat out of these systems, things can go from a gas to a liquid and from a liquid to a solid, and we call that process condensing and freezing. And so I want to kind of name these processes really fast. When something goes from a solid to a liquid, what do we call that? Well, we call that melting. And when something goes from a liquid to a gas, then we call that evaporating. Let's say we cool that gas off and we return it to a liquid. That's called condensation or condensing. And then if it goes from a liquid to a solid, we call that freezing. There is this one little special case where things can go straight from a solid to a gas, and that's called sublimation. But for the purposes of our lecture today, we're not going to talk about sublimation. We're just going to talk about melting and freezing and evaporating and condensing. All right. And so the first thing that we're going to examine is what happens to solids when we add heat. right? And solids of all different kinds of materials. And so as things are heated, generally they tend to expand. Now water is the exception to this rule, and we'll talk more about water next time. But generally, as things heat up, they tend to expand and get bigger. And then as they're cooled, they tend to shrink back. Now, this is an ideal world where things would expand and shrink proportional to one another. In the real world, things tend to expand a lot and then shrink only a half or a proportion of what they've expanded. And so they don't tend to condense or shrink back to their original volume. Things have this elastic barrier or elastic property that they can't always go right back after they've been deformed. But for our purposes, we'll pretend that they do. And so as things are heated, they tend to expand. Depending on what we're talking about, the type of object being heated, we can talk about a volumetric expansion, or we can talk about a linear expansion. And that's these two formulas. So V is for volume and L is for linear expansion. These are pretty much the same formula, just depending on what we talk about. This beta and alpha are coefficients depending on the material. So if I'm talking about like aluminum, and let's say I have an aluminum can, I'm going to use the volumetric formula. And I'll go to your table on page 379, right, which is pictured right here. I'll find aluminum. And I'm talking about volumetric, and so this is the coefficient that I'll use, right? If I'm talking about a volumetric expansion of concrete, then I'll use that. However, sometimes we talk about linear expansions. A lot of building materials are like rods or beams or things that expand in a linear form, not really a volumetric form. And so let's say that I have a big steel beam that's going into a building, but they're building it in the middle of the winter in Rangeley, so that beam is going to shrink and expand with those temperatures. If it's a steel beam, I will be looking at using a prefix of a coefficient of linear expansion, and I'll use the steel one from this table. This table is always available to you. I don't expect you to memorize the values. In both of these formulas, L sub I and V sub I are the initial length and the initial volume. And then all we do is we multiply that coefficient, the original version of that material, by the change in temperature. I want to make this really important note that anytime you see delta T or delta anything in a formula, it is the final version of that minus the initial version of that. If something is heating up, this value is going to be positive. But if something is cooling off, then that delta T is going to be negative, and we're going to ultimately see a shrink in linear length or the volume of that substance, right? And so just be really careful about what values you're plugging in for the final temperature and the initial temperature. Right? And so I want you to just go ahead and jot these two formulas down, and we're going to work through a couple of examples. And I am going to tell you volumetric or linear, but in the problems for homework, you're going to have to decide on your own. All right, so let's pretend there's this really crazy weather day in Rangeley, and the low is negative 20 degrees Celsius, and the high is 30 degrees Celsius. And so we're looking at an overall temperature change of 50 degrees Celsius. Now, last lecture, I told you that the T in any formula was not Celsius, but Kelvin, right? The formula to convert Celsius to Kelvin is the temperature in Celsius plus 273, and then that's our temperature in Kelvin. So if we want to convert these to Kelvin, we can. However, I also at this point want to make a note that if something changes by 1 degree Kelvin, by 1 Kelvin, then it also changes by only 1 degree Celsius. And so when I look at this delta T, this change in temperature, well, that's going to be the same whether or not I use Kelvin or whether or not I use Celsius. It doesn't matter. And so I can just do the subtraction, and I can say there's a difference of 50 degrees Celsius, so that is also 50 Kelvin. Right? And if you don't feel comfortable for that, that's okay. You can go through the conversion and do it that way. Okay, so there's a crazy day in Rangeley with this 50-degree fluctuation over the course of the day. By how much does a 1 meter by half a meter by 1 centimeter section of concrete sidewalk expand? And so we are looking at a sidewalk section, right? And we'll say it's 1 meter by 0.01 meters by 0.5 meters. And so the initial volume of this thing is going to be its length times its width times its height. And so let me just start here. I need to find the coefficient of volumetric expansion for concrete. And I look in my table, I find it there. So it's going to be 36e to the -6. The volume of this thing is going to be 1 times 0.5 times 0.01, which I will find to be 0.005 cubic meters, so 0.005. And then that temperature difference is 50 Kelvin or 50 degrees Celsius, your choice, which gives me an ultimate volumetric expansion of 9e to the -6 cubic meters, right? And so what we find is that as the temperatures fluctuate throughout the day, concrete actually does expand and contract, right? Expands when it's heated, contracts when it's cooled, and that's actually why you have the little cracks in the sidewalk, right? It's just to allow space for those things to expand and cool as needed without damaging the sidewalk. If we didn't have those cracks, as they expand, these things would kind of rift and break in the middle, and we'd have really messed up sidewalks. You see this in your daily life. Anytime you go over a bridge, there are these gratings for thermal expansion, and they've kind of got these little finger projections that allow this concrete to expand in the summertime and contract in the wintertime without the whole bridge falling apart. Okay? You've also probably done this, where you've got some lid that's really hard to get off, so you run it under hot water, and what that does is it kind of expands this lid out volumetrically to make it a little bit looser and a little bit easier to unscrew. You might have seen thermal expansions on railroad tracks. Railroad tracks are really difficult. You've got these long steel beams, and as they expand and contract, they don't always go right back to where they're supposed to be. And so if you have a really hot day, they usually send people out to monitor the tracks so that we don't get this, because if we don't know that's there and a train comes along, then this happens. Okay? And then I'm sure that everybody, if you've never driven over a bridge and you've never tried to get a lid off something and you've never seen train tracks like this, I'm sure that everybody has actually used this thermal property of matter for your boo-boos. So when you get a boo-boo, your body tends to swell up, and so you put ice on it to contract that and kind of minimize the swelling within that so that you can still have a better range of motion in whatever you've gotten a boo-boo on. All right, so let's try one more. Let's try a linear expansion one. Let's say these steel railroad tracks are made of 10-meter long steel rods or beams. By how many degrees Celsius would the temperature raise for them to have to expand by 1 centimeter on either side? And so I'm looking at these things that are 10 meters long, and ultimately they're going to expand by 1 centimeter on either side. And so they're going to have an ultimate expansion of 2 centimeters. So our delta L right here is going to be 0.02 meters. Right? I'm going to set that equal to, okay, then the alpha. Well, we're dealing with steel, so I'll go to my handy dandy table and I'll find steel. And I know this is a linear expansion, so this is what I'm going to be using for alpha. 12e to the -6. The original length of that was 10 meters. And I'm asking by what temperature would it have to increase. So I will divide both sides by these two. Divide both sides by these two. They cancel on this side. And I'm left with a change in temperature of 166 degrees Celsius or 166 Kelvin. Both work, right? Because they're equitable scales. Alright, so we know that as things heat up, they expand. I also want to tell you about this other kind of property, thermal property of matter, which is specific heat. Depending on the type of matter, things heat up at different rates, right? Every substance in our world has a specific heat value, and that is the amount of heat, right, heat energy that it would take to raise the temperature of whatever that substance is by 1 degree Celsius, to raise 1 gram of that substance by 1 degree Celsius or 1 Kelvin, right? Again, because they're equitable scales. The specific heat of something is represented by the symbol C, and that's important because you're going to see it in a formula coming up here soon. And again, like the coefficient of linear and volumetric expansion, these values are given to you. They're on page 381, and this is the table that you're looking for. And so as you look in this table, I want you to make a note of what has the lowest value of specific heat and what has the highest value of specific heat. All right, and as you're looking, you should see that lead has the lowest value of specific heat, and liquid water has the highest value of specific heat. Right, and so we've got all the solids and then all the liquids right here. Lead is very, very easy to heat. It doesn't take a whole lot of heat energy to actually increase the temperature of that substance. But for liquid water, we actually have to put a lot of energy into it to increase the temperature of that water. And you're very familiar with this because you probably have boiled water to cook, right? And so in general, the higher the specific heat number, the more energy is required to actually heat that object. Water has a very, very, very high specific heat compared to things like metals. But then even within the metals, let's say it's a lot easier to heat gold than it is to heat aluminum, right? Aluminum has a higher specific heat. I also want to make note of the specific heat of ice, right? Water is a solid, and liquid water. They are different, and when you're solving problems, you're going to use these two values depending on the situation that you're talking about. And I'll give you some examples coming up. All right, so the specific heat equation, the heat, right? The heat that is necessary to heat some mass of a substance, and then you'll use the specific heat of that substance by some temperature difference, so delta C or delta K, right? Either one works. This is the amount of heat that it is required to raise some mass of a material by temperature T. And then this, the C, you will always get from that table, depending on the substance. So if we're talking about aluminum, right, then you'll use the aluminum specific heat. If we're talking about a mammal, then we'll use the mammal specific heat. All right, so let's practice. How much heat energy would it take to raise the temperature of 8 kilograms of water by 30 Kelvin? Well, let's start with this equation, right? We don't know how much heat, but we do know the mass of the water, that's 8 kilograms. The specific heat of water, we are talking about liquid water here, so we're going to use this specific heat, the 4190. So we'll use 4190, right? And then how much do we want to change the temperature of that? We want to change it by 30 Kelvin. And then once we multiply that out, we'll have the heat in joules that needs to be added to that system in order to heat our water. To do that, so we will do 8 times 190, 8 times 4190 times 30, and that's going to give us 1,005,600 joules of heat need to be added to that system in order to heat that amount of water. And to give you an idea of how much water I'm talking about for that big number, 8 kilograms is about 16 pounds of water. So that's a good bit of water. And so this answer, yes, makes sense. Right? The high specific heat of water is really interesting. We are made of mostly water, but it also accounts for things like water in our oceans. Right? And so the high specific heat of water actually contributes to the climates of places around the water. So if you live on a lake or by the ocean, what we see is that the temperatures are more stable in that area. The highs aren't as high and the lows aren't as low in some place by the ocean. Whereas in the desert, like Rangeley, we get really high highs and really, really low lows, and we get these big fluctuations in temperature on a daily basis because we don't have the water there to absorb the heat energy. Water is able to absorb a lot of that heat energy on the ocean side, thus regulating the daily temperatures in those areas. This is also interesting for us as mammals. Most animals and plants are made of mostly water, and so it takes a lot for us to change our temperature. For us specifically, we see a natural temperature change. Our body kind of kicks into high gear. Whenever we get sick, we get these fevers, and so I don't know if you've ever heard this, but there's this old wives' saying called "starve a fever, feed a cold." And we're going to figure out what that means, right? And so if you have a fever, you want to starve it out. And that's what we're going to focus on in this problem. So whenever you get an infection, your body raises its temperature in order to kill whatever's making you sick. Living organisms have a really small threshold for temperature changes, but your body can safely raise its temperature by a few degrees, and hopefully that'll kill out whatever's going on inside of you. But it takes a lot of energy for your body to run a fever, which is part of why you feel so tired when you have a fever. And so what I want to do is take a look at how much energy it would take for you to raise your body just by 1 degree, right? It's not even a really serious fever. And so I'm going to use the formula that Q is equal to M specific heat of a mammal by the change in the temperature. And if you want to take a second to kind of go ahead and solve this out, let's assume that your mass is 70 kilograms. And you can pause the video and go ahead and look up your specific heat and figure out the problem. I'm going to go ahead and solve it out. So we're going to say this person is 70 kilograms. That's my standard go-to for a person. The specific heat of a mammal is 3,400. And we're looking at raising your temperature, your delta T, by 1 degree Celsius. Right? And once we do 70 times 3,400, we find that it takes 238,000 joules just to raise your body by 1 degree. Now, if you're eating on a regular basis, then this energy is readily available for you to run a fever. But if you're not eating on a regular basis, then your body's going to start burning that energy from fat. And so really, this is kind of irrelevant, right? Your body's going to get that energy however it needs. But this is part of why you feel so very tired when you run a fever, right? You need to rest so that your body can do its business and take care of things. And you don't have other energy outputs going other places, drawing away from your body's natural defense. All right. So earlier we talked about this idea of adding energy to a system in order for it to go from a solid to a liquid to a gas. So far we've only talked about increasing the temperature of a solid or increasing the temperature of a liquid. And that's that whole, it requires whatever amount of heat to change a mass by a temperature. But it actually takes a lot more energy to change something from one state of being to another. And so if you take a look at this graph, what we see is that as the temperature goes up, right, if we have like some ice and we raise the temperature of that ice, once that ice gets to 0 degrees Celsius, then it kind of just hangs out there, even though we continue to put energy in. And you can see energy down here on the x-axis. So we continue to put energy in, but the temperature doesn't change. And so there's this idea of, well, it takes a lot of energy to actually melt all that ice at 0 degrees Celsius to turn it into water at 0 degrees Celsius. But once it's all turned into water, then we can begin to heat that liquid, and then we find another phase change. And so when that liquid gets to 100 degrees Celsius, right, it's ready to boil. And what we find is that that liquid kind of hangs out at 100 degrees, until it starts to turn into steam, and then we can increase the temperature of that steam. And so there's heat required to heat a substance, right? But to make it change phases, to make it go from a solid to a liquid, or from a liquid to a gas, or the reverse, from a gas to a liquid and a liquid to a solid, then that actually takes a lot more energy, right? And we're going to talk about that as being the heat of transformation. There is a formula for that, but it's a little more specific than just the heat that we need is the mass times L. L is the heat of transformation, but we're going to be really specific here because it's different it's different for melting than it is for vaporization, and we're going to look into that a little bit. But we'll kind of specify this. The heat needed to melt or freeze something, right, that first phase change, is L sub F, and L sub F stands for the heat of fusion. There's a nice neat table in your book for these values. Again, you don't have to memorize them. And then L sub V is for that second transformation, boiling or condensing. And so this actually stands for the latent heat of vaporization, used to boil or condense something. And so what we see is on page 384, we've got these different substances that we can change from a solid to a liquid to a gas. If we're moving from solid to liquid or liquid to solid, we'll look at the heat of fusion. And if we're moving from liquid to gas or gas to liquid, we'll look at the heat of vaporization. So it really just depends. The other thing I want you to note when you look in this table is that for a given substance, like water is what we'll use most often, the heat required to take water from ice to liquid water is a lot smaller than the heat required to take liquid water to boiling water, vaporizing it. The other thing I want you to make a note of is that sweat on our bodies is actually a form of losing energy or a phase change because it evaporates. And it is really, really high. And so you might just want to jot that down either in your book or in your notes because it's not included in this table. You do want to go ahead and dog-ear this page though, because we'll be coming back to it here in a minute. And we're going to try and work some examples. I'm particularly interested in this because this is something that your body does naturally. It actually uses energy from your body. And we talked about this a little bit the other day in class. All right, so to associate this with a graph, moving from a solid to a liquid, we have to use the heat of fusion, and moving from a liquid to a gas, we have to use the heat of vaporization. And again, that heat is going to be equal to the mass of whatever we're trying to phase change, and then LF or V, depending on what kind of states we're trying to move it to. All right. If we're looking at taking something completely from a solid to a gas, so these are solids, liquids, and gases. If we're looking at running the full spectrum, then we're going to have to look at the heat that it takes to heat the solid to melting, and then the heat that it takes to actually melt that solid, the heat it takes to raise the liquid to boiling point, and then the heat that it actually takes to vaporize whatever we're looking at. All right, so let's talk about sweating. The human body can produce approximately 30 grams of sweat a minute, which is like 30 milliliters of sweat, if you know what 30 milliliters is. At what rate is it possible to exhaust heat by the evaporation process? So if we can max make 30 grams of sweat, I'm going to go ahead and convert that, and that's 0.03 kilograms. And the heat that we will lose due to that evaporation is equal to the mass of whatever's evaporating. And in this case, 30 grams of sweat multiplied by the heat of vaporization because it's evaporating. And for sweat, that's 24 e to the fifth. Right? And so whenever we sweat 30 grams a minute, and we're looking at losing 7,200 joules per minute, in terms of energy loss per minute due to sweat. right? If we convert this to calories, what we're looking at is about 17 calories, right? The kind of food things you're interested in per minute. If you think about sitting in a sauna for 20 minutes, then at that rate, you're burning 342 calories over your entire 20-minute sauna sit. And so even when you do sit in a sauna, you are burning calories, but if you were to do anything else for 20 minutes, you'd surely burn a lot more calories, because not only are you sweating, your muscles are using energy to do work. All right, and so then let's talk about a very sweaty person. Let's say that a very sweaty person loses about half a kilogram of water over the course of a workout. How much heat energy did they exhaust during this process? Half a kilogram of water is about a pound, right? And so they're looking at losing a lot of water. Again, what we'll do is that the heat lost is equal to the mass, whatever's evaporating, and so we'll use that L sub V for sweat. It'll be half a kilogram multiplied by the heat of vaporization for sweat. And what we see is that a person will lose about 120,000 joules if they lose about a pound of sweat in a workout. Now, a pound of sweat is a lot, right? And this is just the heat lost due to evaporation of sweat. This does not account for the actual energy that they burned running or biking or whatever the case may be, right? This is just for the sweat. All right. And so let's take a look at what would be more energy intensive, melting 1 gram of mercury or melting 1 gram of lead. So for both of these, the mass converts to 0.001 kilograms, right? And the heat required is the mass times the heat, and now I said melting, so that implies going from a solid to a liquid, which means I'll be using the heat of fusion, so L sub F. So then for mercury, it will be 0.001 times 0.11 e to the fifth, and then for lead, it'll actually be 0.001. And then the heat of fusion for lead is 0.25 e to the fifth, and I don't even have to do the math to figure out that heating the lead is going to be a lot more energy intensive than heating the mercury, because it has a higher heat of fusion, right? All right, so let's talk about the whole spectrum. So we're going to use both of these formulas. We're going to use the Q, M, and then L sub F or V. And then we're also going to use that specific heat formula, MC delta T. So we're going to take ice and we're going to vaporize it. And that's not sublimation. That's us going through the whole process of melting the ice and then boiling the water. So let's say that we have 30 grams of ice and it's at 0 degrees Celsius. So the heat to melt that, just melt the ice, we're going to use that ML, and then we're going to actually use the heat of fusion because we're melting. And so for us, it's going to be 0.03 kilograms of that times the heat of fusion for water, which is going to be 100. Oh, no, I'm sorry. Let me go back. I accidentally used the heat of fusion for sweat. All right. And so times the heat of fusion for water, which is 3.33 e to the fifth. Okay. And that's going to give us 9,900 joules of energy just to melt the ice, right, and turn it into liquid water at 0 degrees Celsius. So then we're going to have to apply some energy to bring that 30 grams of melt water to 100 degrees Celsius. And so we're looking at using this formula. So we'll do Q is equal to MC delta T. And it's still 30 grams of water. But now we're going to use the specific heat of liquid water, 4190. And then we're going to be raising it by 100 degrees Celsius. So our delta T is 100 degrees Celsius. And once we multiply all of that out, we'll find that that process takes about 12,000 joules of energy. And then we've got to vaporize that 30 grams of water. And so this is a phase change again. So we'll go back to using our phase change formula, except now we're going to use the heat of vaporization for water. It's still 30 grams of water, so 0.03 kilograms. And we're going to use the heat of vaporization, which is much higher, because remember, it's much more energy intensive to change something to a gas than it is to change it to a liquid. And that's going to be about 67,000 joules. Okay? And so the total energy requirement to completely vaporize that ice is going to be the sum of all three of these processes. And so we'll take that initial energy of melting the ice, and then the energy that it took to raise the temperature of the water, and then finally the energy that it took to vaporize that water, and we'll get a grand total of about 90,000 joules, right, for that whole process. And so again, you'll use this formula for heat when you're doing a phase change, and this formula when you are just increasing the temperature of a substance, but not to the point of a phase change. Okay. Which leads us to our last idea, is that of calorimetry. You see the word calorie in here? Because this is actually a process that your body goes through, and we can convert calories to joules, heat in and heat out. What we see is that when we have heat in these two systems that begin coming in contact with one another, heat is going to flow from hot, so whatever the hot substance is, to the cold substance until they reach equilibrium. And we talked about this last time. That equilibrium is where they have equal temperatures, and so the final temperature of this heat exchange is going to be it's going to be the same for both materials. What we find is that the absolute value of system 1, so we can say this is like the coffee in this picture, because heat is going to go from the coffee to the ice, right, from hot to cold. And I choose this because I love iced coffee. So the heat's going to flow from hot to cold, which means this is actually going to be a negative Q, and this is going to be a positive Q because it's gaining heat to its ice system. What we find, though, is that the absolute value of the heat gain and loss is the same, right? There's 100% conservation between these two systems. And we're always going to just kind of incorrectly assume that this exists in its own little world and that no heat is actually being lost to the environment, right? We know that in reality heat is being lost, but we're going to pretend that it's not. So the net change in heat between two systems that begin to mix is always going to be 0, because if one system is losing heat, then conversely the other system is gaining that heat until they are at equilibrium, at which point heat transfer stops, and so the net heat loss or gain is 0. Okay. Alright, so we can actually do this, and if I remember to buy Doritos, we'll actually do this in class. Let's pretend that we have a sample of burning Doritos, and it's found to increase the temperature of 10 grams of water from 30 to 40 degrees Celsius. If the transfer is complete, which means no heat is lost in the environment, then how many calories of Doritos were burned? And so you probably know from eating Doritos or chips that they're pretty high calorie, and they're so high calorie and greasy that you can't actually physically set fire to them. But we're going to pretend that all of the energy from here, all of the heat energy from the Dorito, is being applied to the water and none is lost. And so you can actually figure out how many calories food is just by burning it and letting it heat water. I'm going to define this as heat being lost from the system, and so that's actually going to be a negative value. And then for the water, heat is being gained by the system. Okay. So what I'll do is I will take these values and I will set them equal to each other. Right? And remember, it's really the absolute values that are equal. But as a side note to me, I know that the Dorito is the one losing heat. So I could take these things, I can set them equal to each other. And I can say the heat from the Dorito. So maybe I need to specify. We'll say Q of the chip system is going to be equal to the heat gained by the water system. For the water, it is just water that's being raised, and so I'm going to use the specific heat one. Right? I'm not changing a phase of water. I'm just melting it, and so how much water did I have? I had 10 grams, which is 0.01 kilograms, and I'm going to multiply that by the specific heat of water and the temperature which I changed it by. And what I'll find is that I get 419 joules of energy to do that. But that's not the question that I asked. I asked how many calories of the Dorito were burned. And so I've got to take this joules and I've got to convert it to calories. So I'm going to erase all the work from my slide. Erase all. And I'm going to do 419 joules. And then I know that there's 4.2 joules in 1 little calorie, and I know that there's 1,000 little calories in 1 kilocalorie, which is what we measure food in. Multiply across the top, multiply across the bottom, and you'll find that we only had a fraction of a calorie in that chip that we burned, and so we're actually talking about a very small quantity of Doritos to do that. All right. We can also talk about this in terms of adding two systems, and so I'm going to go back to my iced coffee system. If I have 10 grams of ice that are right at freezing, and I add them to 50 grams of hot coffee, which is initially at 70 degrees Celsius, what's the final temperature of the coffee? Well, I know that these two things are going to exchange heat from the coffee to the ice until they are equal in temperature. Right? I know that the ice is going to melt, and so there's going to be, for the ice, there's going to be a melting heat, and there's also going to be a warming up the liquid water from the ice heat, right? So the ice is going to melt, and then it's going to warm until it's ultimately equal to the coffee heat. And so the coffee is going to decrease in temperature, the ice is going to increase in temperature until they're equal and they reach equilibrium. All right, so for the ice to melt, and this is a phase change, I will use MLF, the heat of fusion for melting, and I've got 1 gram of ice, heat of fusion for water, plus, and then it'll still be 1 gram, but it'll be water at this point, specific heat of water, right? And then I know its initial temperature was 0, so for the whole delta T part of that equation, and I'm sorry, MC delta T, it's going to be T final minus 0, which is really just T final, right? And then that's going to equal my 50 grams of coffee. Coffee is pretty much just water, so I'll use the specific heat of water. And then it's going to be the temperature final minus 70. So its initial starting temperature was 70 degrees Celsius. And I don't know the final temperature, but I do know that the final temperature of both of these is going to be the same. And so my job is to simplify, 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 and then get the temperatures on one side and all the whole numbers on the other. So I'm going to be solving for the final temperature. So when I simplify this, I'll get 3,330 joules to melt the ice, plus 41.9 times the final temperature is equal to 209 times the final temperature minus 70, which was the starting temperature. I'm going to add 70 to both sides. Okay. And I'm going to subtract 41.9 t from both sides. T from both sides. I am going to erase all the link on the slide, so watch out. Go ahead and write down the work. All right, and what I wind up with is that I've got, let's see, 3,400. So I went up with 3,400 after I added 70 to both sides is equal to 167.6 T sub F after I subtracted that 41.9. To get the temperature final by itself, I need to divide by 167.6 on both sides. 0.6, those cancel. And the final temperature of both the coffee and the ice is going to be equal to 20.28 degrees Celsius. And then does that make sense? Well, yes it does, because the coffee started at 7 and it's cooling off. Alright, this brings us to your homework, so have fun. These are all conceptual, and this is going to be quantitative, so have fun, and I will see you in class on Friday. I want you to come up with at least one problem you need help with. And it can be from any of the chapters. Need help with. It can be from any of the chapters, and I will sit down with you as an individual and help you out with that problem. All right, happy studying.